to another live science show with me, Lara, from Theatre of Science. We're going to talk about the birth of the universe. It's a double story timer because the birth of the universe is quite a heavy topic. So we're going to start with the story time, we're going to end with a story time, and in the middle we're going to do some activities with elastic bands and or balloons. So the Big Bang. What is it? The Big Bang is a theory, it's the best theory we have at the moment for how the universe started. Basically, that a tiny little particle went and the universe came into existence. Anyway, I'm going to explain to you about the Big Bang. First of all, it's story time, isn't it? I've totally failed. I was trying to get Einstein here because you are about to meet him. Okay, it's nearly 95 years ago, this month actually, 1915, Einstein, obviously, publishes his theory of general relativity, which included the gravitational field equations. There they are, aren't they beautiful? I don't understand them either. It was called one of his greatest achievements, and this is Einstein, so these equations were good. They predicted the existence of black holes. That's predicted them. Just used maths to say that black holes were probably out there in the universe, and they are. They explained and predicted the very strange orbit of Mercury around the sun. They said that clocks tell the time differently in space, and they do. It's very good. But it also predicted something which very much troubled Einstein. These equations say that space should be changing size, getting bigger or smaller. Now, like everybody else, Einstein was absolutely sure that the universe was a static thing. That means it wasn't moving, it had been there forever, it would be there forever. And he was sure that he must have made a mistake. So what he did was, he added a fudge to his equation. In the same way that, like, if you perfectly measured a shelf for your wall and then you put it up and it didn't look quite right, you maybe would just like stick another little bit of wood underneath or something. He kind of did that. He added this thing in pink, which is called the cosmological constant. And this makes the equation predict an unchanging, unmoving universe. Phew, there you go. Now, actually, a few years later, a Belgian cosmologist and Catholic priest called Georges Lemaitre published a paper explaining brilliantly why he thought the universe was expanding and like solving this equation. But it was in a very obscure Belgian paper. He even went as far as saying that he thought that the further away bits of the universe were from Earth, the faster they would be moving. But no one listened to him. I mean, they didn't even argue against him. They were just like, what is this? Looks boring. Not bothered. Poor Georges Lemaitre. We'll come back to you later. Someone who you might have heard of because he's got a brilliant telescope named after him. Someone called Edwin Hubble then made a fabulous discovery. So another thing most people thought in these days was that the whole universe was just our galaxy. So obviously we live on Earth, which is going around the sun, Mercury, Venus, Earth, Mars, all that lot. That is called our solar system. But our solar system is just part of the Milky Way galaxy, which is a big collection of stars. Edwin Hubble realised that some stars were 10 times further away than the stars of the Milky Way. He basically discovered that he confirmed that there were other galaxies beside our own. This was like massive headline news at the time. Suddenly, the Milky Way galaxy wasn't the only galaxy in the universe. And Edwin Hubble noticed something else, right? The light from all these different galaxies that he'd seen, it looked like it was being stretched. Hubble realised that the galaxies are moving away from us. And not only that, the galaxies furthest away are moving faster than the galaxies close to us. At this point, Georges Lemaitre is like, excuse me, I did... And finally, his paper gets translated into English. And everyone's like, oh, right. So this idea that the further away a galaxy is, the faster it is moving away from Earth, is known as the Hubble-Lemaitre law. And it has massive consequences. It was used as evidence for the Big Bang. So we'll do a little activity now to look at why that is. All you need for this activity is an elastic band. If it's one that you can write on, that's good, but if it's just one of those little ones, doesn't matter, you can make marks. And a biro and a felt pen and piece of paper, or actually just an elastic band, pen and paper basically. If you're wondering how Einstein felt about being proved wrong, he was actually, as you would expect from someone who worked really hard and cared about physics, he was delighted. He was like, that makes much more sense. And he called his little fudgy constant my biggest blunder. Although actually we think that it might now explain dark energy, but that's a totally different thing. Let's do this activity. I'll show you what the Hubble-Lemaitre law actually means. So, get an elastic band, and I have been unusually prepared today. I have done this already. On your elastic band, if you can write on it, draw a little H, and that is going to stand for home galaxy. That's like the Milky Way galaxy. So we'll pretend that we are standing on this H, and then draw on the elastic band 2 little lines, one quite close to the H and one far away. So you're drawing an H, which is the home galaxy where we are, and then draw a line which is another galaxy quite close to us, like the Andromeda galaxy, that's our neighbouring galaxy, and then draw one quite far away, okay? And then get a piece of paper and put your elastic band next to it, and just mark those again on the piece of paper. Mark those again on the piece of paper so you've got them as reference, because we're going to stretch the elastic band. So I'll put my H there, and I'm putting a line there because that's where my close galaxy is, and a line on the paper there because that's where my far away galaxy is. Okay? And when you've done that, keep your home galaxies, your little H's, lined up with each other and stretch your elastic band. You see that properly? Like this. There we go. What happens? Can you see that the galaxy that was quite close to us has moved a bit further away, but the galaxy that was far away from us has moved a lot farther away? Okay, so imagine that we were standing on the H. If, say, the universe was expanding, stretching out like an elastic band, what we would see would be galaxies close to us moving a little bit away, moving away like quite slowly, and galaxies far away moving away faster. It's kind of like, you know, like if you get 2 and you double it, then you only add 2 more. Whereas if you get like 10 and you double it, then you've added on 10. You see what I mean? It's a bit weird. But basically this is what the Hubble-Lemaitre law said, and it was seen as proof that the universe was behaving a bit like an elastic band, that the universe is stretching. Very important to note. Here, I've done something else on the other side. Oh no, I've done something on this blue one as well. Look, it's important to note that doesn't mean that our galaxy is at the centre of the universe. You can put your little H anywhere and galaxies closer to it, and it works the same way. I'll show you while you're doing this at home. So let's try that here. This time I'll put the home galaxy on the edge, and then that galaxy is close and that galaxy is far away. And keep those H's lined up. So it works the same way. So it's important to note that whichever galaxy you were in, you would always observe this weird thing, that the galaxy is far away and moving faster. So it's not that the thing with the Big Bang, I'll come back up to see you now. The thing with the Big Bang is people imagine that because there was this Big Bang, that the universe is now all stretching away from where this one bang was. But that's not really what it is. All it is it's like an elastic band or a balloon. It's like the entire universe is stretching, so wherever you are. Let's do the balloon thing, okay? So if you've got a balloon that you can write on, you could get your balloon now and put some little dots on it. I can't really write on this because it's black, but I'm going to use these happy birthdays, okay? Imagine that the balloon is the universe and that these happy birthdays and these stars are galaxies, like our Milky Way galaxy, okay? And then blow up the balloon and let's see what happens to the distance between the galaxies. The galaxies are social distancing, says Oscar. Yes, exactly. All right. what happened to the distance between my galaxies as I blew up the balloon. I'll do it a little bit more, look. I don't know why I blow up balloons live. It always makes my head go funny. Can you see what has happened? So space has expanded, stretched, and all the galaxies have moved away from each other. Now, the Institute of Physics, the oracle on physics, they wouldn't like this model. They do a similar model, but they do something else, which I thought was a bit faffy for you. But they say to get little dots and to stick them on the balloon and pretend that the dots are the galaxies, all right? So we're still pretending that the balloon is the universe. Are you okay with these words that I'm using? So the Earth goes around the sun, and all the planets go around the sun, and that's our solar system. Our solar system is planets going around one star, but there's loads of stars all clumped together in our galaxy, which is the Milky Way galaxy. So all these little dots now, we're going to pretend that they're galaxies, and we're going to pretend that the balloon is like the space between them, like the universe. Hello, Tabitha. And let's blow it up again and have a think about why the Institute of Physics say that this is what you should do. What's different between this model and the one with where we just say the happy birthdays of the galaxies? Ready? Oh, April, sorry. Can you use something else if you haven't got a balloon? Yeah, you could keep using the elastic band, to be honest. It's just the same, really. This is just like a 3D way of doing it. So now, forget about the happy birthdays. Space has expanded, but what's happened to the galaxies? They've stayed the same size. Oh, hello, Martha. You're a bit late. Thank you, Izzy and Liz, give me an answer. Do the Institute of Physics not like it because the galaxies expand too on the balloon, but not just the stickers? Yes, exactly. So what is actually happening is that the galaxies are not expanding. The Milky Way galaxy isn't stretching apart. It's only the space between the galaxies that is stretching. Why is that? Why is that? Why aren't the galaxies expanding? I'll give you another example. So another model that people use is the idea of raisin bread. Like if you get a lump of bread dough that's got lots of raisins in it and you put it in the oven, then the bread dough will rise and rise and the raisins will move apart from each other. But the raisins will actually stay the same size. So the reason the galaxies are not expanding is because of gravity. Gravity, very strong force, which holds things that have matter together. Yes, exactly. Listen, Izzy, you are on fire. Yes, it's a gravitational pull. Yeah. So the Milky Way, stuff that's got a lot of matter, is all clumped together. But space is stretching. Right. Shall we actually look? So that was one piece of evidence for the Big Bang. I will tell you now what happened in the Big Bang. And then we'll look at how the Big Bang Theory got like totally sealed, because this was like strong evidence, but it wasn't absolute proof. There's another bit of evidence which we'll look at in story time. But first of all, let's actually look a bit more at this Big Bang, shall we? Here we are. I need my whole whiteboard for the Big Bang. Let's get some lids off these pens. So it was George Lemaitre, actually, incredibly, even before we had all this actual evidence, who said that he thought the universe was expanding because of Einstein's equation. And if the universe was expanding, says George Lemaitre, then it makes sense that at some point it must have been much, much, much smaller. So George Lemaitre says that he thinks the universe began as a teeny tiny, like infinitesimal teeny weeny, much smaller than any atom, a teeny tiny particle, and that 13.5 billion years ago, suddenly a huge amount of energy was released. Big Bang, not a great word for it, because it's like someone very cleverly said, the Big Bang, it wasn't really a bang. Like a bang would be a noise, and there wasn't any noise because noise would require sound to travel to your ears, and there were no ears. There was not even any space. So picture this little particle, okay? You're imagining it like in the blackness of space, but that's not right, because space doesn't exist yet. Space is in the particle, and you're imagining like time going by, but that's not right either, because time is like inside the particle. Time was created by the Big Bang. So it's not that this little particle exploded and that bits of these particles are like flying across the universe. What happened is this particle, suddenly a huge amount of energy was released, and this particle started to stretch. And it's still stretching. So imagine like, you know, like how if you ride down a hill on your bike then when you get to a flat bit, you can carry on going without pedaling, okay? Because you've gained some energy from the hill. It's like that, except 13.5 billion years later, you're still not having to pedal. Like the universe, the Big Bang is still happening. The universe is still stretching all around us, but it started with this little particle. So let's carry on. First of all, a split second after this enormous release of energy, everything had so much energy. So I keep telling you that everything in the entire world is made of atoms in all my lessons, right? These particles are sort of held together by forces, but they had far too much energy at the beginning of the Big Bang to stick together. So at the very start of the Big Bang, all we have, oh, I can't believe that's run out already. All we have are teeny weeny little particles. Some of them are quarks. Oh, you'll learn about quarks if you do A-level physics. They have like different flavours. They're amazing. These teeny tiny little quarks just buzzing around. And we have also photons, little particles of light. But there's so many teeny tiny little particles in the universe that have so much energy that the light can't shine, okay? These little packets of light, these photons, are just like bouncing around of all these particles. So the very beginning of the universe is incredibly hot and also very dark, kind of foggy, okay? But about 1/10 of a 1,000th of a second after the Big Bang, because the universe is stretching out, and so all that energy is like spreading out, the universe is getting cooler. Finally, these quarks are calm enough to bond together to form particles that you might have heard of called protons and neutrons, the things right in the middle of this atom, yeah? So finally, quarks are hanging on together to make protons and neutrons, and then 400,000 years after the Big Bang, eventually, teeny tiny little particles that again you might have heard of, thank you Sadaf, called electrons. Finally, 400,000 years after the Big Bang, electrons are calm enough to begin orbiting these protons and neutrons, and we have atoms. Now, this is very important, remember this for story time. Atoms don't really interfere with light, so finally, these poor little photons of light that have been bouncing around, they can travel in straight lines, and light can shine. So 4,000 years after this enormous release of energy, the universe is suddenly this bright and beautiful place. And about 1 billion years later, all these atoms are finally calm enough to start like gathering together in clouds, and then they start fusing together and releasing huge amounts of energy. And when particles do that, it is called a star. So like our sun is a star. But actually our sun isn't one of these stars, because these are super early stars. Eventually these stars fuse together and together and together. So these simple little atoms like hydrogen and helium, they get put together into even bigger atoms inside these stars. So like the oxygen that you're breathing in, the calcium in your teeth, that might have been made inside one of these really early stars. They're building up particles to get bigger and bigger and bigger, and then when the stars have run out of fuel, they explode, supernova, release even more energy, enough energy to create even heavier atoms like gold and silver. So now, billion years after the Big Bang, there's massive clouds of all kinds of beautiful particles floating around that we're familiar with, and eventually they clump together again and new stars begin to burn, but there's also lots of beautiful exotic particles swirling around which can clump together around the stars and form planets like ours. Whew, so there we go. So that takes us from particle to Earth. Any questions? Do let me know, do let me know. Right, so that's the Big Bang. It is called a theory. Oh, Edgar asks, were there quarks before the Big Bang? Well, Edgar, I looked into it. Scientists say that asking what was before the Big Bang doesn't really make any sense, because like there wasn't any time and there wasn't any space. But right at the end of the show, I will tell you what we think might happen to the universe next, and that might answer your question. Yeah, so the fact that the universe expanding is one piece of evidence that this happened, but it was another piece of evidence a bit later on that really made everyone think, okay, yeah, this must have happened. I will tell you about that now in story time. In 1960, in America, a company called Bell Labs built a 6-metre horn-shaped antenna. I would usually say look it up, but to be honest, what I have here is almost photograph accurate. This big antenna was built to be used with a very early satellite system, and it was designed to detect radio waves. So just like there are waves on the ocean, all around us, through the air, right now, waves are passing through us. So light is a wave, and you can picture it as a wave on an ocean. So this distance here that I've done in green, the distance between each crest is called the wavelength. So light has quite a short wavelength. This antenna is looking at radio waves, which have quite a long wavelength. They carry less energy. Obviously, how radio works, they travel through you all the time. They don't hurt you, it's fine. So 4 years later, the satellite that this antenna was working for, a new satellite came about, which was better, and the whole thing became obsolete. Oh dear. This was great news for two scientists called Penzias and Wilson, because they were allowed to use this beautiful antenna to study the radio waves that travel in the space between galaxies. But just like when you're using a mobile phone, you get a load of crackling in the background and it's really annoying and it stops you working properly. When Penzias and Wilson looked at the data that they'd collected from this massive antenna, they found that there was this, like, what you call a sort of annoying background noise. It was actually microwaves. So microwaves are halfway between radio waves and light, a bit more energy than radio waves, a bit less energy than light. Microwaves seem to be travelling from all different directions and hitting this antenna and making it that the scientists, they couldn't really see their data properly. They couldn't really find the radio waves. This was incredibly annoying. They tried everything to solve this problem. They even thought that maybe birds were pooing on the antenna, which of course they were, because birds do that. So they spent ages and ages clearing all the poo off the antenna, but it didn't make any difference. It still didn't work. They were totally stumped, these two poor people who only wanted to study radio waves. At the same time, this is the 60s, a team at Princeton University, led by a scientist called Robert Dick, was studying the very, very, very young universe, the primordial universe, the bit between the Big Bang and a few thousand years later. Now, at the time, people knew that galaxies were moving away from each other, but the Big Bang Theory, it hadn't been totally accepted. Now, Dick's thinking was, here he is, that if the universe is expanding, then at some point it must have been a lot closer together, and it must have been a lot cooler. It must have been a lot hotter as well. So if now it's kind of spread out and cool, at some point it must have been very hot and close together. And heat doesn't just disappear, okay? Just like when you blow out a candle, heat doesn't just disappear. It what we call dissipates. It like spreads out into the air. So Dick thought that maybe the heat from the Big Bang that would have been a light wave when it first got emitted, maybe that would still be observable today as like background radiation. It would have been spreading out ever since the universe began. So Dick said he calculated that by now it would probably be about a microwave. It would have stretched. And actually at the time he was building a radio antenna to try and detect it. When he received a message from Penzias and Wilson saying, "Oh, we've got these microwaves getting in the way of our radio antenna. It's so annoying." What? Dick was totally staggered. He knew straight away exactly what it was, and he explained it to Penzias and Wilson. And they all wrote papers that were published very quickly afterwards, with Penzias and Wilson talking about what they'd seen, and Dick basically explaining what it all meant. And then in 1978, the Nobel Prize in Physics, the Grand Master Ultimate Award for brilliant work in physics, went, of course, to Penzias and Wilson. Oh, is that fair? Nobel Prizes are only given for discoveries. They're not given for interpretations. So as one scientist put it, Dick received only the admiration of his colleagues. It's quite sad because he died in 1997. Never having won a Nobel Prize. Although I did learn when I was researching this that Jim Peebles, who was on Dick's team, he did win the Nobel Prize actually last year, 2019, basically for the work that he did with Robert Dicke. So that's nice. And another nice thing is that you remember Georges Lemaitre? Hello, excuse me. He found out about Penzias and Wilson's discovery of what we now call the cosmic microwave background radiation, just before he died. So Lemaitre learned that the Big Bang theory is now the accepted theory of how the universe began because of this evidence. So well done, George. You got the recognition you deserved in the end. Right, now that's nearly the end, but I want to very briefly tell you what might happen at the end of the universe. And also, actually, I didn't do this in the show I did yesterday, but there's also quite a nice thing you can do with an elastic band. If you've got an elastic band on you, draw a little wave on it. Because that's a bit weird. You know that bit in Storytime about how light that was emitted when the Big Bang first began is now a microwave radiation. I'll show you. If you draw a little kind of light wave on an elastic band, there we go. So imagine that that's the wave that was created when the Big Bang happened. It's been travelling through the universe, and the universe has been stretching and spreading out. So now that wave looks like that. Microwaves. And I guess if the universe carries on for long enough, then eventually it'll become radio waves. So there you go. Elastic bands, explaining the universe. Yeah. The other thing I should say very quickly, if you've ever turned on your TV and instead of a channel, you've got that like white sort of staticky fuzzy on your TV, that is caused by the cosmic microwave background radiation. So there you go. How is the universe going to end? Well, we don't know. It depends on the size of, it depends on its mass. So in the same way that if you throw something really heavy into the air, it just plops back down. But if you threw something that was lighter than air, like a helium balloon, into the air, it would just carry on rising. If there is a lot of mass in the universe, then eventually it's going to get to a certain point, and then gravity is going to suck it back in again. And that will be the end of the universe that we call the Big Crunch. Or if it hasn't got enough mass, it could do what someone else said and just sort of spread out and out and out and out and out. And someone said disappear. Yeah, exactly. Just become so spread out that, you know, all that energy is just gone. Or if it's like got a sort of perfect critical mass, then it might become absolutely static. We just don't know. We don't know. The interesting thing about the crunch is that some people are saying, well, maybe that happened before. Maybe we've talked a little bit about oscillators, like, you know, if you imagine like a clock ticking, things that go from side to side to side to side. Maybe the Big Bang has happened before, and that the universe is an oscillator, and it expands, and then gravity makes it go into a crunch, and then it expands again, and then it goes into a crunch. So there you go. Happy Sunday morning, everybody. I'll leave you with that thought. Maybe we live in a giant crunch bang situation. I don't think it'll affect any of us day to day. That is the end of Science Show Live's universe episode. Bye.